So today we want to talk about the Rayleigh-Plateau instability in terms of the Navier-Stokes equation. When we do an analysis related to the Navier-Stokes equation, we usually first write down all the related functions and then write our continuity equation and then write our final Navier-Stokes equation. And today when we are talking about the Rayleigh-Plateau instability, we consider a case where there is a certain cylinder and it will someday break down into tiny droplets. So it would be natural or it would make a lot of sense if we are using the cylindrical coordinate system. So let's write down our perturbations first as a function of omega and k, where omega is the growth rate of our instability and k is the wave number of the disturbance in the z direction. Here we will use something called epsilon here, and epsilon is just our amplitude of the perturbations. But we have to remember that this epsilon, this tiny epsilon, is much, much smaller than our initial R0. So if you look at the picture to the right, you will see the steady state and the perturbed state. And the steady state, we have this nice radius of R0, a surface tension of sigma, and rho, the density, and P0, the pressure. But if we have a perturbed state, we are going to have a slight change, a very slight change in diameter. So, or radius. So we can say that this our slight change in radius can be expressed as R0 plus this perturbation amplitude. We will say that sigma remains the same and rho remains the same. However, we will see that this pressure term will be slightly perturbed by the amount of P. Okay, so now let's look at how this perturbation functions will be written. We will first say that R is a function of R0 plus epsilon e to the omega t plus ikx. But in our case, we will be putting a slight change to our equation because this will actually be expressed in the z direction. So we are taking our r function as a function of z. Okay? So, and then the other terms, the ur, the uz, and our p are each the radial component of the perturbation, the axial component of the perturbation, and the perturbation pressure. You can see that all these terms are accompanied by the same term, exponential omega t plus ikz, where k is the wave number of the disturbance in the z direction. And therefore, we can also think that the corresponding wavelength of these perturbations is going to be 2 pi over k. Now, using our ingredients, our functions, we are now going to write down our continuity equation. So our continuity equation goes as follows, as you can see on the bottom of this picture. Okay, we have these rho and round t, and all the other terms accompanied by rho, ur, u, theta, and uz, because we are going to use the cylindrical coordinate system. So using mass conservation, we can first erase a few terms here, and let's see. Well, we are going to assume that we only have a velocity in the radial and streamwise direction, so ur and uz is not going to be 0. But we will see that we have this u theta component, and u theta component is going to be 0 because we have a velocity only in radial and streamwise direction. Also, we will be considering axisymmetry. Therefore, there's a certain term with something round theta is going to go to 0 because it is axially symmetrical. Okay, so using these terms, and lastly, we will consider that in the cylindrical coordinate system, we will have a steady compressible flow. Therefore, we are going to get rid of our round rho round t. And let's see. And we are going to say that this rho term is going to be constant, as we have first seen our picture. In the steady state and the perturbed state, there is going to be no change in our density. So if you get rid of all the terms, we can get rid of this u theta either by our axisymmetry or by the velocity not being in the theta direction. And therefore, we only have to consider these two terms when we have to write down our continuity equation. If we summarize this, we are going to end up with a nice, round round r, right, plus ur over r plus something called round round z equals 0. But using the principle of linearization, we are going to rewrite this part as simply uz. Therefore, we are going to have round r, plus ur over r plus uz equals 0. Okay, that's simple. And secondly, we are going to look at our Navier-Stokes equation, which is much more complicated, way more complicated than our continuity equation. But our Navier-Stokes equation, we first have to assume our axisymmetry. Therefore, something over round theta is going to be 0, and we only have the velocity in the radial and streamwise direction. Therefore, ur and uz are not 0, but u theta is going to be 0. And thirdly, importantly, we have negligible viscous and body forces, which means that we are going to neglect this gravity component. So this gravity component is going to be 0, gr, g theta, and gz is going to be 0, and anything inside the brackets of this mu term is going to go to 0 because we do not think of any viscous forces. So now let's get rid of everything we don't want. And let's also get rid of, we will in the future also get rid of all the higher order terms that we do not have to consider. Okay, let's see. If we get rid of everything, we are going to have, firstly, we are going to have no terms in the viscous bracket. So these three are all going to go to 0. And we do not have any other body forces, so these terms are all going to go to 0. And if you look at the theta component, as I said, u theta is 0, so anything related to round theta or u theta is going to go to 0. So let's see, this guy is going to go to 0, this guy is going to go to 0, this is going to go to 0, this 0, 0, 0, 0, and 0. Okay, and we will also say that this guy is gonna go to 0. Right, that's about it. So in our equation, we have only these three components for the r equation to the left hand side, and the only pressure term survives in the right hand side. And for our zeta or z, we are going to have only these three terms at the left and only the pressure term at the right. And we can further simplify this by saying that our epsilon is very small, therefore it is appropriate to consider linearization. Therefore, we do not have to consider these terms because if you actually calculate like round round r, using this equation here, so if you do the round here for ur, and you will get the relationship that it's going to be a second order term with respect to epsilon. So it's going to be very small, so we are going to consider that this term is going to go to 0. And similarly, these terms are all going to go to 0. Therefore, we have a very simple equation at the end of our analysis, only related to round t and pressure terms. We do not really have to write down the theta term because all the terms in the theta equation go to 0. Okay, so we will first write our r and z, and m is just from our mass conservation, which is equivalent to our continuity equation. So this was what we just derived from our continuity. So we have these three very nice looking equations. And now how are we going to solve these equations? Well, we are first going to substitute these functions in the yellow box, inside the Navier-Stokes equation and the continuity equation. Okay? So our first step is to determine the left and right terms for every single equation we got here, RZ, and M. For our equation, we have on the left-hand side, round UR, round T. So if you calculate that with respect to this yellow box equation here, UR, we know UR, and UR is a function of T, right? So if you do round UR, round T, we get R times R times omega times this exponential term. And if you do the same thing for round P, round R, we are gonna get this equation, which is expressed as dp dr and the exponential term. Okay, so we can equate these two equations later and get a corresponding relationship. And secondly, let's look at our z equation. So round z, round t is gonna be, if you calculate using this uz in the yellow box, we're gonna get z times omega times the exponential term. And if you do the same thing for round p, round z, we are gonna get p times ik times the exponential term. And lastly, we can now do an analysis for our mass conservation equation. So we have these three terms here. So round UR, round R is going to be round large R times the exponential term. And UR over R is simply going to be R large R over R times the exponential term. And UZ, as we can just plug in this yellow equation here, is going to be Z, where Z is ZR times exponential term. And you will notice that all these terms, 1, 2, 3, 4, 5, 6, 7, all these terms contain the exponential term. So if we are going to equate the left-hand side and the right-hand side, we can just cancel out this term, knowing that it is not going to be 0. Okay, so what happens here? Well, if you equate everything for number 1, equate for number 2, and add these up to get 0, we can rewrite everything like this. Okay, you notice that the exponential term is not important anymore. So for r, we get omega r is minus 1 over rho dp dr. And we can write similar equations for z and m, where z, it's omega z equals minus ik over rho times p. What's important about the z equation, it might not look very important here, but you will notice that it does not contain any derivative term. Therefore, we can simply say that p and z are now expressed as a simple functional relationship with respect to the parameters rho, omega, I, and k. And we can rewrite this by saying that p is minus rho omega over ik times z, which is going to be the key part of solving this equation. And m, our continuity equation, reduces into dr over r times ikz equals 0. And when you just intuitively look at this equation, you see that in the m equation, you see in the mass conservation, we have a term related to z, and in the r direction, we have this dp dr term. So using this z, we are going to unite these two equations of r and m, which is going to be the most quintessential important step of our solving procedure. Okay, so let's first look at our r direction. We have omega r is minus 1 over rho dp dr. And if you actually take the derivative of this term with respect to r and solve this equation, so you're going to do ddr on both terms, okay? ddr on left-hand side and right-hand side. We are going to get this first equation, which is going to be omega times dr minus 1 over rho dp dr second derivative. Okay? Okay, and we also know that from this equation, we can also earn the second relationship using this z term. So I just told you that this P and Z are related by this function. Therefore, dpdr can be rewritten as minus rho omega over ik dz dr, which is going to be pretty simple, expressed by omega over ik times dz dr. Therefore, we can say if we express everything in terms of dz dr, it's going to be ikr because this term goes to the left and the omegas cancel out, right? Okay, so we get these two relationships. Number one, the relationship between d large R dr and the second derivative of p with respect to r, and secondly dz dr as a function of large R. And we can now plug these into our mass conservation, our continuity equation. So we have this purple equation here, and we will do the same process. We will take the dr to the left hand side and the right hand side, and we will arrive at this complicated looking equation, the second derivative of r with respect to r plus 1 over r, and all these tiny little terms that accompany this. And you see that, well, these terms arise because we are doing the second derivative to the left hand side, and you see that this r large R over r is going to be d dr large R over r is simply going to be expressed as this term because large R is a function of r in itself, and when you say that large R is constant and derive the 1 over r term, it's going to come out as minus 1 over r squared. And we know that z is also a function of r, so it's going to be ik dz dr for our last term. And you don't really like this shape of the equation with all these r squares and r's in the denominator, so we are going to multiply all the terms by r squared. Therefore, we get this nice looking equation with r squared multiplied in the left hand side and the right hand side. Okay, so what else can we do? Well, we see this dz dr term here, right? And what is dz dr? Right, we know from our first relationship that dz dr is simply ikr. Okay, so we can now finally get rid of this annoying z term. And dz dr is going to be ikr. Therefore, if we plug in everything, we are going to get this final equation, this final relationship. So we have this r squared term and the derivative and the r squared term, and the first derivative, and a simple function related by 1 plus k r squared times r. This is simply plugging in this r term and the ikr term into the brackets. And if you look at this, if you study differential equations, you will see that this can indeed be solved in a certain method, and the solution is going to be called the Bessel function of the first kind. Now in our second video, we will look at how we are going to apply the Bessel functions into this equation and equate this using a few other equations with respect to pressure to find the final relationship between the perturbed pressure and the perturbed radius. And we will consequently solve our critical time and critical length as a function of rho, r, and surface tension.